Hello everybody and welcome back to another Wise video. Today we're going through an IGCSE Edexcel Chemistry Paper 1C. I will link the paper in the description of this video. This is a 2022 paper if I'm not mistaken, but you can see the specific paper in the description of the video. And yes, I'm sorry for not uploading in so long. I've been quite busy with assignments, but right now I'm able to get a few videos in your exam season. So yes, let's go right into the video. So first things first, remember your periodic table is always at the start of your chemistry paper. So very important, you'll need it for basically most of your questions. So it should be of much use to you. So let's have a look at question 1. This question is about mixtures and compounds. This box gives some methods to separate mixtures. Choose methods from the box. Okay, identify a method to separate a single food dye from a mixture of food dyes. So remember, when we hear dyes, what we should instantly be thinking is chromatography, paper chromatography. But here it just says chromatography, so we're going to take what it says from the box and say chromatography for an easy 1 mark. Okay. Now we see gasoline from crude oil. When we hear like crude oil, and we know the different fractions of crude oil. You should know the different fractions of crude oil if you're studying double and triple, I believe. But just in general, as soon as you hear crude oil, you should know it's to do with fractional distillation, because that involves separating the crude oil into its different fractions. So, fractional distillation. Okay. Identify a method to separate water from copper 2 sulfate solution. Now, we can see each method must be used once, more than once, or not at all. So it could be any of them, but it's very easy to rule out what it can be. I mean, it can be chromatography because we're not dealing with dyes, and we're not dealing with a mixture of dyes or a certain paper. It's not fractional distillation because we're not talking about crude oil, and it's definitely not crystallization because we can just do that by deduction. So we know it has to be simple distillation, and if you've seen the copper 2 sulfate water separation of copper 2 sulfate, you should know that it's simple distillation as well. So that's an easy 1 mark as well. That's an easy question. So now question B. This diagram represents a molecule. Explain why this molecule is a compound. Now, for these types of molecule compound questions, it's very easy, but they're looking for something kind of specific. The mark scheme isn't very wide, so make sure you remember this. If they want you to identify why something is a compound, you have to say 2 different elements. In this specific case, it is 2 different elements. If there was more, you can just state how many there is. And if you guys can't tell, the elements are identified from the different circles. So that's 1 element, and that's 2 elements. And we're seeing that there's 2 different elements in this case. If there was a 3rd circle here, we would say 3 different elements. I'm sure you can tell that. So that's not it though. So we see 2 different elements that are, this is the important part, chemically bonded together. So 2 different elements that are chemically bonded together. And that's a nice way to get both marks there. Couple other ways you can get marks are by saying 2 different atoms. I still recommend saying 2 different elements. And you can also give a description of bonding, but once again, wouldn't recommend that. This is the easiest way to identify a compound. 2 different elements chemically bonded together. Okay, so now the molecular formula of a compound is C3H5N3O9. Say the number of different elements in this molecular formula in this compound. So, number of elements, remember, it has nothing to do with a subscript. It just talks about the different elements there. So we can see there's carbon, hydrogen, nitrogen, oxygen, and that is 4 elements. So don't get confused, just know there's 4 elements. There we go. So, determine the number of atoms in the molecule. Well, unlike the other one, this does have to do with the subscript. So, the little numbers, the subscript you can see under the bottom right of each element, that is how many atoms of each element there is. So, if we add that together, we'll get it. So, we have 3 plus 5, which is 8, plus 3, plus 3, which gives us 11, plus 9, which equals to 20. So we know that our answer for the number of atoms is 20, and there we go. Question number 2. This question is about rusting. A simplified formula for rust is Fe2O3. Name 2 substances needed for iron to rust, and this should be very easy for you. So remember, rusting is basically oxidation, so we know oxygen is involved, and it happens in the presence of water because we know it forms hydrated Fe2O3. So we need oxygen and water for this to happen. Now, give the chemical name for rust. Well, like I just said, first of all, the important part for rust is that it is hydrated. So before we write the actual chemical part, we put hydrated, right? And then remember that it is iron 3 oxide. And remember, the 3 refers to its oxidation number. And if you guys couldn't remember the that it's iron 3 oxide, remember that from Fe2O3 we can use drop and swap to figure out that it is iron 3 oxide. And yeah, I'm sure you'll know how to do that. Okay, now for question number 3, what type of reaction occurs in the rusting of iron? Now, I've also answered this question already unintentionally, but yes, a very simple question. It is oxidation. And yeah, I won't even go through the deduction for that because we should all know that it is oxidation. Now, some iron objects are coated with a layer of zinc to prevent rusting. Name this type of rust prevention. Now, you may be a very common trick question this is actually. So the correct answer is actually galvanizing or galvanization, right? Now, what's commonly put is sacrificial protection. But that's actually not the type of rust protection. It's just the way in which, it's just the manner in which it's protecting it. So actually, this is not the wrong answer, right? That the manner in which zinc is used to protect iron from rusting, that's what you call galvanization. So remember, if it talks about zinc being used to protect iron from rusting, always talk about galvanizing or galvanization. Just an important note. So if you said sacrificial protection, unfortunately, that would not get you any marks for this question. Now it says, explain how this type of rust prevention continues to protect iron when the layer of zinc is damaged. Now, this may be a bit of a confusing question, but it's really not too hard. So, first we have to think about how it protects iron. So, zinc is more reactive than iron, right? And we would know that if we don't even need to refer to this reactivity series because we learned this as part of the syllabus. So you should know that zinc is more reactive than iron. And because of this, zinc reacts with oxygen before iron, preventing rusting. Right? Important things to know. Instead of saying zinc reacts with oxygen, you can say zinc is oxidized, or zinc is corroded, whatever. But just say before iron or instead of iron, right? You just want to say that in place of iron, zinc is the one that reacts with the oxygen. And another thing to say is, a common thing that I've always seen is that people say zinc rusts instead of iron. This is completely false because iron is the only element that you refer to as rusting when it is oxidized, right? No other element has that property. You just call it corrosion or oxidation, right? So iron is the only one that can rust. So you want to only say zinc oxidizes before iron. Don't say zinc rusts before iron because that would be completely incorrect. So this is the perfect answer, but not perfect, but this is the general answer, and there are many other ways you can say this. But yeah, pretty easy question. Give 2 other methods used to prevent iron from rusting. Completely simple, basic 2 marks here. Even without any knowledge of chemistry, you can immediately think of painting. What would protect iron? Just an outer layer of paint to protect it. And then another one that could, the second one is kind of hard actually, because it's kind of a minor part of the syllabus that they're asking questions about, but I will give you options that you can talk about. So one could be plastic coating. Coating the iron in plastic. It's pretty self-explanatory to see how this would prevent it. Also greasing or oiling the iron. Another one could be chromium plating. Remember, a lot of these aren't in syllabus, so if you never heard of these before, don't be afraid. And another one that you should know is sacrificial protection. This is the one that I expect you to say if you come to this question, because I feel like this is the one that's most commonly explained. But if you want to say any of the rest, it's completely okay. But sacrificial protection is the one that I recommend because it's the easiest to remember in my opinion. And we have one more, which is cathodic protection. And there we go. So these are a plethora of options for you to choose for methods of preventing iron from rusting that are not galvanization or painting. But yeah, I generally recommend saying sacrificial protection. Okay. Next question. This question is about states of matter, and this box gives us changes of state. Complete the table. Oh wow, this is... Okay. So, name of change of solid to liquid. Wow. Melting, we all know that. Solid to gas, we're going to say a simple sublimation. and liquid to solid, we're going to say freezing. So if you're having like trouble remembering sublimation, I just recommend that the ones that we all know, which is melting, evaporation, freezing, condensation, these are the ones that we commonly know. There's two more that you do have to know, which is sublimation and deposition. But deposition is much less commonly mentioned than sublimation because it's no, it's just you more rarely see deposition. So you'll frequently see sublimation, and when you see sublimation, just think of solid to gas. Just think of something subliming, and then think of solid with the S. So sublimation starts with an S, and solid starts with an S. So solid, sub, and then limation. So limation, think of elimination. So elimination of solid, so solid to gas. So solid is eliminated, and it forms gas. So that's just an easy way to think about it, but it should be pretty simple for you. I'm sure you all know what sublimation is. And yeah, you could even just elimination. You can see solid to gas. You know it's not condensation. You know it's not freezing, not melting, and evaporation. We know it's not that. And cooling. That's just not even any of them. So you can't even consider that. So it has to be sublimation. Okay, when ammonia gas and hydrogen chloride gas mix, they react together to form a white solid known as ammonium chloride. The equation for this reaction is this. A teacher soaks a piece of cotton wool in, yes, another piece of cotton wool in concentrated hydrochloric acid. The teacher places the two pieces of cotton wool at opposite ends of the glass tube at the same time. After several minutes, a white ring of ammonium chloride forms. So here's the white ring. Here's, since it's from each of the sides. Okay, after several minutes, say the name of the, say the name given to the spreading out of gas particles. Okay, and just before we start answering this question, I just want to say that this is one of the most common questions I've seen. Because when I did my GCSEs, I faced a question that was quite similar to this, not only in like my mock examination, and also a couple of my unit tests. So this test is pretty common, and even my teacher showed me questions like this in class. It's a common question, and even since this is from a recent paper, it shows that this question still commonly pops up. So take extreme note to how I answer these questions. So state the name given to the spreading out of gas particles. Well, they don't give you the most accurate or like the most in-depth description of what it's talking about, but the answer is diffusion, and I'm sure we can all get that. Diffusion is basically the spreading out of gas particles. Okay. State how the diagram shows the particles of ammonia gas are traveling at higher speeds than the particles of hydrogen chloride gas. Now, how well can we tell it? Well, we can see that these, the white ring is not equidistant from the cotton wool with hydrochloric acid and the cotton wool in ammonia solution. So we can say the white ring forms further away from the ammonia showing, actually it's thick, so we don't do the same thing else. So yeah, the white ring forms further away from the ammonia or closer to the hydrochloric acid. Simple as that. Okay. Gas particles travel at high speeds. To give a reason why the white ring of ammonium chloride takes several minutes to form. Okay, this is a pretty simple one. Well, we know of the concept of Brownian motion from not only our chemistry but also physics, but it basically tells us that gas particles are moving randomly. So the gas particles are moving in random directions. Okay, that's one reason. So even though they're moving fast, they're moving randomly. So there's no guarantee that they're going to react with each other in the time, in that time. Okay, and now another one. Gas particles are collide with each other. That's another major problem, because it's going to, even though they're traveling very fast, the reactions are going to happen instantly because they're constantly colliding with other particles as well. And they also collide with the walls of the tube. So they're not just moving forward in a constant motion, they're colliding everywhere, crashing into everywhere, moving randomly, and then it takes several minutes, and then finally they react, forming the white ring. Okay. Concentrated ammonia in solution and concentrated ammonium chloride, hydrochloric acid are corrosive. Give one safety precaution the teacher should take, and Okay, safety questions. You should have like a bank of different things you can say, just stored in your head so you can just recycle in for every safety question. Remember, some questions you'll have to apply different safety principles more specifically, but generally you can just say the same things for every safety question. So, simple thing as safety goggles. Or wear safety goggles, actually, that's a better way of saying it. Wear safety goggles. Wear gloves. Wear a lab coat. Something as simple as that. And these are just ones when you're talking about corrosion stuff. Safety goggles, gloves, lab coat, very easy ones to say. Okay, now this is the copper powder. Okay, yes, very good practical. And the teacher uses the apparatus to find percentage of oxygen. Yes, oxygen and argon. Okay, this is the teacher's method, and then we see this method here. So I'm sure we've all seen this practical before because it's in the percentage of oxygen unit when we're calculating the percentage of oxygen in air. So instead, in syringe A and B, we have air, and you push it into different syringes, and then the copper powder reacts to form copper to oxide, and yeah. So we've seen this practical before. Let's see how it's changed. We know that this is a mixture of oxygen and argon now, and that's essentially air. It's just trying to trick us. And yeah, so it's saying step one: heat the copper powder. Heat the copper powder. Push the okay. So you can read this practical here. So it's missing like a lot of key components from air, like nitrogen, mainly nitrogen, and the 0.04% of carbon dioxide. But basically, everything else, oxygen and argon is there. So we can just take it in. Don't get confused. Just take in the fact that we've seen this practical before, except instead of air, we're using a mixture of oxygen and argon. Okay, so now we read the practical and we can see, give a reason why the copper powder is heated. Well, if we studied the practical before, which we all have, we know that the reason it's heated is to increase the rate of reaction, to give the particles sufficient energy to react. One mark, I just made sure that I was made sure that we got the mark there, so I wanted a bit extra, but yeah. Okay, state why argon is unreactive. Very, very, very simple active. Very simple question. Argon has a full valence shell. So just like argon has a full outer shell of electrons. Because yeah, we all know that is a noble gas. So it'll have a full shell of electrons, so it can't give or accept its electron readily.